Well, good morning, everyone. This is the so manyest rendition of my weekly webinar. Today I'm going to talk about solar chargers, DC and AC, solar panels a little bit. But what I'm trying to aim for with this presentation is to just explain how the solar charging works, how solar panels work, what you have to watch out for, when to choose DC, when to choose AC PV. There is a lot of content already on our website in regards to training with solar chargers. So, but I'll mention that as well. So that's why I thought rather than doing double things, I just add to what we have already. So that's how this presentation came about. And in a few weeks, I will do a lot more on systems and things like that. So all the system related questions and stuff, please wait a week or two for that. I'll start my screen share. 1 second. Share screen. PowerPoint. 1 second. Yeah. So everyone can see the PowerPoint, I think. I assume so. Okay.
Yeah, that's right.
Yeah.
It's okay.
Solar chargers and PV inverters. Like I said, so we're going to talk about the basic solar system. So basically with that, that's just one slide basically. Solar panels and solar arrays. How do they work? Why do they work that way? DC solar chargers, AC grid inverters, so that's solar charger too, but then on the AC side, and then DC versus AC, so what's better and why, when to use which one, and then a bit about other training material we have available. So starting basic solar system. Yeah, I thought I might as well put this slide in here to familiarize everyone with all the different components. So what I have on this picture here is a solar system, a Victron system with some solar in it basically. So what you'll see is your inverter charger. So I assume that every Victron system has a multi or quattro inside in the system. Now you can also have solar systems with just some DC loads, but for the sake of completion, I just add a multi or quattro. It's connected to either a generator or grid or both. It has a monitoring device, ideally speaking. It's connected to a battery. So these are all the non-solar parts. So that's basically system stuff. And then there's two options for solar. One is the grid inverter and the other one is the DC inverter. The DC solar charger. The charge controller DC connects directly to the battery and the AC one connects to the AC. So that's the main difference in between the two. Like I said already earlier, we're just going to concentrate on, basically on this one, and the solar panel. So on the highlighted stuff here. How to put it together in a system, we've already talked about a little bit and we'll be talking in the next few weeks about as well. And then the other thing is how to program and set it all up. And that's being discussed at length in the training modules we have online. So I'm not going to get too much into programming either because there's no point doing double things. Okay, so, well, the first solar component in the system is the solar panel, otherwise it wouldn't be a solar system. How do they work? In a way, you have an LED. Everyone knows an LED. If you put power into an LED, light comes out. So basically what a solar cell is the reverse of that. So it is the LED type materials. Only now light shines into the component and electricity comes out. So it does that by, say, light shining in. It's a bit like a diode. So you've got two layers of material, an N-type and a P-type material with a isolating junction in between. Photons, light contains photons. Photons hit this material and they start releasing electrons to jump across from the N-type material to the P-type material. And as soon as electrons move, that means you have current. So these electrons want to go back to the original layer where they came from, and they have to go via the circuit. So electrons move into the little wire and then you create electricity. So that's basically, it's a bit similar to a transistor or an LED, only the other way around. So you shine light on it and that will make the electrons move. So that's how a solar panel works. So one item like that is called a solar cell. Solar cell makes about 0.5 volts, and that's pretty standard. That's just inherent to the technology used. It's the same as an LED. You need 0.3 or 0.6 volts or a diode to make it conduct. Same thing with solar panel. If you put photons in there, once you start exciting the electrons, you will get 0.5 volts coming out of it. But 0.5 volts is not enough to actually do anything with. It's not suitable for battery charging. You can hardly run anything off it. Doesn't have much power either. So what they do with solar panels is they take those solar cells and they put heaps of them in series. So you could hear in like series, so it goes around and around and around all the way till here. So you end up with, for instance, this picture is one of a panel with 36 cells in series. So now you have 36 cells, each do 0.5 volt, it's series, so you add all the voltages and then you get 18 volts. So that's how solar panel makes voltages. Of course, if you put more cells in series, you get higher voltages. So you have the 36 cell panel, you've got a 60 cell panel, you've got 72 cell panel. So the cells, the more cells you can actually see, there's different. So each little block here is a cell. So there's more and more. Same here, cell, 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 cell. So more in series means higher voltages. There might even be other configurations. There's a lot of innovation happening with solar panels all the time. So this is sort of the standard set, 36, 60, and 72. They all have their specific voltages. So the nominal voltage, that really comes from the time when a solar panel was connected straight to a battery. So an 18 volt panel, so that's a 36 cell panel, once you load it up, will drop down to 12 volts. So that's a 12 volt nominal panel. That's where that comes from. So originally they made 36 cell panels to connect to a battery. Then they thought, well, we have 24 volt batteries. We also make 24 volt panels. So that's how these panels come about, 72 cells, double the amount of cells. And then for residential solar, and also because people started connecting actual panels in series, and then grid feed inverters came about. So then people needed a higher number of cells or different number of cells for whatever their inverters could deal with, what sort of voltage. So that's when the 60 cell panel and other panels come about. The panels, well, this is a little screenshot from one of our data sheets. We sell panels as well. We don't actually make panels ourselves. We basically select really nice panels and get them to stamp our name on it. We don't actually have a solar panel factory. So the reason we sell panels is because sometimes it's hard to get certain configuration panels, especially the smaller ones are becoming harder and harder to get. So the 20, 30, 40 watts, you can get them easily, but then, yeah, you have to go to China and then they make you buy a whole container. And if you only need a few panels, so that's basically why we stock panels partly. It's just easier because we can bulk purchase them. And it's a bit like a stop in between the customer and the Chinese panel manufacturers in other countries. So all these panels, they have a power, a nominal power. That's how many watts they make. So that's what you can run off them. So 5 kilowatt system, that sort of things. That's looking at the power. Then you have voltage ratings. So VMPP, IM and VOC, open circuit and maximum power voltage. So VMPP is your maximum power point voltage. That's that 18 volt I explained earlier. So that at that voltage, the panel makes the most power. So basically that's the ideal voltage. They say maximum power voltage. Yeah, so that's what it's called. The other one is open circuit voltage. That's basically like it says, if you have a panel and you do not connect a load to it, you just have the two leads coming out of it, it makes a voltage and you put that panel in the sun. And if you put your voltmeter on there, you will measure 22.6 volts. These open circuit voltages, I think from memory, they're specified at 25 degrees Celsius. If your panel is -5, or this morning 2 degrees, the open circuit voltage is actually higher than in the spec sheet. So you always need to, then taking open circuit voltage in consideration, where is your panel located? And how cold does it get at night? And is your panel already facing the sun in the morning? If the panels are cold, sun comes up, shines straight away on the panel, then the open circuit voltage might actually be a bit higher than what the spec sheet says. So we always sort of advise to stay about 10% away from that. So that's the voltage ratings. And the last ones are the current ratings. Maximum power current, that's the current where the power is maximum. And the short circuit current. And short circuit current is if you, opposite of open circuit, short circuit. So you connect the two positive and negative leads coming out of the panel. The panel will make, your small panel will make 1.19 amps. So that's that's also important to know. So to make sure your wiring is right and that sort of things. So that's basically its maximum current it can make. But ideally you don't short circuit your solar panels anyway. But that's where your wiring needs to be based on. So or data sheet, but also squillion of other manufacturers' data sheets. Always consult the data sheet before connecting your solar panels to other equipment, because you want to know what they do exactly. Well, we already mentioned maximum power point. So if you look at the current and voltage graph of a solar panel, so you have current on this side, voltage on that side. This line is voltage time current, the orange, the purplish sort of line. So at so current and voltage. The blue line on this side indicates the power. So the blue line follows the power as voltage and current changes. So each panel has got this ideal moment where the current graph is at the top. That's the maximum power point. So that's the ideal sweet spot of the panel where it can make the most power. So you take that point and then go down, and then you find the voltage and the current and the voltage where that appears. And this shaded blue area, that's basically your amount of power you create. So that's why it's important to sort of know, and I'll explain a bit later why that becomes important. So that's basically what's behind those graphs. Now, if, for instance, you have a hot panel or partial shaded panel, that means that some cells are completely in shade, so they don't make 0.5 volts anymore. So that's when the voltage can drop. But also if the panel gets really hot, the voltage drops, because that 0.5 electronics voltage, that band cap voltage, I think it's called, or something like that, that becomes lower with heat. So therefore a hot panel will have less voltage. So let's say this panel was at 25 degrees Celsius or 20, whatever the testing conditions were for the data sheet. Now this panel sits in 30, 40 degrees, or the panel is that hot, then your voltage will get less. So also that power point will change. So that maximum power point is now over here instead of, so that's moved to somewhere else. So it's important to know where the power point is to fully utilize your panels. If you get less light, remember that light contains photons. Photons create electron movement. If there's less light going into the panel, you get less photons, because less light is less photons, and they excite less electrons. So the electrons are less, and that means that the current is less. So if it's cloudy weather, if the sun angle is wrong, so you have early, like late in the evening, your panels face slightly away from the sun or something like that, then you basically get less light, less photons hitting the panel, and then you get less current. So again, power point changes. Power point is now here instead of way up there or over there. So this is sort of important to know and what it does. So basically less voltage or less current immediately creates less power, because remember the square was power, so less power than that power. So that's important to know. So how much power do the panels make and what affects power? So it mentioned a bit, depends where you are in the country. I've got map of Australia here. This is the sunshine hours, so how many hours of sunshine in the day. Yellow is 11 hours, dark pink is 0 hours, but well, basically you're looking at Tasmania gets about 3 hours of sunshine, and this is winter in June. So at the moment, probably we just had the shortest day. So that's, yeah, so Tasmania's got 3 hours of sunshine hours on average, taking weather in consideration and stuff. And top end, Darwin has got 10 to 11 hours sunshine. So this is how different it can be. So if you have no sun, you don't get no power out of your panels either. It's logical. It's at night, you also don't get no power out of your panels. So you need to know this when you design the system, for instance, that it matters where you are. So you get weather reasons. You always have bad weather, like in the Netherlands, for instance, or at the moment I have a heat wave, but anyway, or you have seasonal differences. So you are away from the equator. In other words, the winter sun is a lot lower than your summer sun. So summer, you get your sun straight overhead. In winter, it might just go over the horizon in Tasmania or New Zealand or something like that. So that's important. So you have to design, if this is a system that totally relies on solar, you have to design this system for winter basically, or for when it's bad. Then panel orientation and angle. That's basically this thing here. So you have the tilt. So is it like 10 degrees, 90 degrees, or anything in between, 45. And you have if the sun is here, I need something flat, let's say my phone, panel. Ideally, it should shine straight onto the panel. So, but if the panel faces away and the sun hits it at a funny angle, not straight on, but like at a funny angle, like here or here, but not like 45 degrees straight on the panel, that also affects things. So that's basically what this graph here is. So this is your panel lying flat, and that's your panel upright. And this is the difference in between that. So that's 45 degrees is here. So that's the panel going, it'll draw like that, depending where the sun is coming from. Yeah, so the sun is here. If the panel is upright, it might catch a bit of sun in the evening, but the daytime sun, in the middle of the day, it won't catch, of course. So that's what that means. So if your panels are lying flat, you still get really good output, basically. So you still get 90% output. If the panels are exactly right for the sun, like on your roof, 30, 40 degree angle, you get 100%. But if your panels are standing totally upright, you only get 56%. So it also depends how far you are from the sun. Or that's why also solar trackers come in play, because they make the panel follow the sun and stuff like that. Weather, I already mentioned. Cloudiness, shade from tree of buildings. So you have a really big, like double-story house next door, large tree, and a certain part of the day you get a really big piece of shadow on your panels. That will affect things. Dust or dirt, like in the time when you had like all those, I should really clean my panels. Ever since we had all the bushfires, I think I have a lot of crap, sort of soot and other stuff on my panel, so that needs cleaning up basically. Helps as well, might get a few percent more out of your panels. Panel temperature, also important. People at the moment might notice that in winter you get actually much better output than in summer, because your panels are cooler. In the morning you might get more output than in the middle of the day, so that also affects things. So one solar panel quite often not enough for your MPPT solar tracker and or grid feed inverter, so you need to put panels in series quite often. It works the same as with batteries. So if you connect them in series, the voltage goes up, but the current stays the same. If you connect them in parallel, so this is series, that's parallel. If you connect them in parallel, then the current goes up, but the voltage stays the same. And if you need to build a really big array, you do combinations of series parallel. So that's basically what that one. The watts always get added. So 220 watts panels together is 240 watts. So is that combination, and 4 of these panels, no matter how you connect them, will become 480 watts. So that's the same as batteries. So screw or MC4, we have, you can get products with two different solar connections. Sometimes it's screw terminal, sometimes it's MC4 terminal. There is some benefits with either way. Screw terminal is handy because it's quick installation. You don't need to crimp an actual MC4 connector to the wire. Quite often, this drawing I have here, you eventually go to some sort of fuse box. The fuse box has screw terminals, so why should you then again have to clamp another MC4 connector to something? Then go for the screw model version. But if you have a mobile system or where people need to make and break contacts all the time, and or it needs to be ease of installation, or something already became pre-wired, fuse box with wires on it already, then go for the MC4 connections. MC4 is great on the solar panel side. So this is where MC4 is being used all the time, because MC4 is waterproof, it's outdoor rated and stuff like that. But for the indoor connections, and our equipment always needs to be indoor officially, it can be either way. So remember that you need a special crimping tool. Consider using pre-assembled cables. That saves you a lot of hassle, and you know that it's crimped correctly. If you need to make those series parallel connections, you need a special Y connectors. One female, two male, one male, two female. So that's two different ones. And that connects like my previous picture. That connects like this. So parallel connections all go like that, basically. And then one really important, and that's large, it's rated for 30 amp. An MC4 connector should not have more than 30 amps current going through it. So some models of MPPTs have got one of these connectors, some have two, some have three. Make sure that you divide the panels equally among those connectors. Don't put the whole entire array on only one connector, because then you might exceed the 30 amp. So that's an important one to keep track of. And that same counts for all the other connections too. Don't go beyond the 30 amps. And sometimes, especially if it's solar people that are installing a lot of large solar systems, they're used to high voltages. Remember, voltage high, current low. So this 30 amp doesn't come into play, but some of the smaller solar systems, they do have, tend to have less panels in them, lower voltages, therefore the current is higher. And the same goes for the solar cabling, of course. Make sure that that can deal with the current coming from the solar array. Well, that was solar panels. Now we start on charge controllers. Do we need to do a break for questions, or shall I continue?
Yeah, any questions? Please speak up.
This first part was still quite basic.
Yeah, okay.
Maybe after the next one.
They've been answered by Rod and Alexandra, so thank you for your input.
Yeah. Anyway, I'll continue then. So solar panel, like basic solar panel, 12-volt panel, makes 18 volts. You can connect that to a battery. When the battery is empty, it will be 12 volt anyway. It will pull the voltage of that panel down. That's that nominal 12 volt voltage. But once the battery starts getting fuller, the voltage will go more up and up and up and up, and eventually the battery will be overcharged. So therefore you need to have something in between solar panel and a battery. I think one of my, that was the very first solar chargers we started selling, the small little PWM solar chargers. System in a motorhome, I get a phone call, the multi is not working. And I thought, the multi broken, and then anyway, we sent a technician out to the site. It turned out that the multi wasn't broken, but they had used no charge controller. So the solar panel was making the battery voltage 18 volts, and the 12-volt multi will disconnect after 16 or something like that. So the multi was switched off on high voltage rather than, yeah. So that's, yeah. Yeah, so you always need to have something in between a solar panel and a battery. You're not allowed to just connect solar panels straight to the battery, unless you sit there with a multimeter and disconnect them as soon as it goes above 14.25 volts. But yeah, that's not a practical thing. Yeah, so what the battery wants is 14.25 for absorption and 13.5 for float charge. and that's not 18. So yeah, it mismatch. Two different type of technologies for solar charge controllers, DC solar charge controllers, the PWM, and we have the MPPT. Well, first we talk about the PWM, means pulse width modulation. What it really is a switch. So at first when you connect it, it connects the solar array directly to the battery. The battery voltage goes up, and as soon as it hits that 14.25 or 13.5 or whatever you've set it at, might be multiple stage, might be single chains, it depends a bit, or are all multi-stage ones. Then it needs to start limiting the voltage, because if you don't limit, then you get overcharging battery. So how does the pulse width modulator does that? It, like the name says, pulse width modulation. So this little graph here, at first it will give almost the whole entire voltage. It might switch off every now and then, switch off. So this is a certain frequency. There's pulses, really fast pulses. Once the voltage needs to start to be dropped down, it will make the gap in between the pulses bigger and bigger. So the bigger the gap, the lower the average voltage, and therefore that's how we regulate. So we regulate via pulse width modulation. So there's an electronics terminology. So we basically make the gap bigger and bigger and bigger, and then the average voltage drops, and then therefore the battery voltage will stay or drop as well. Yeah, so this process is not totally efficient, because in the beginning of the charge cycle, and I go to the next slide, because it basically in the beginning of the charge cycle, it connects basically the panel straight away to the battery. The panel voltage will drop to 12 volt because the panel is being loaded up. So its ideal point is at 18 volts or something thereabouts. But now we've dropped it down to 12 because we'll be loading it up by connecting it directly, basically. So that means that the maximum, yeah. So the amount of power has become less. So this is the amount of power. The panel can theoretically do this, but because the voltage gets dropped, it will only do this. So the amount of power has dropped down with about 30%, as you can see. So this part is not being used. So there, and so that power goes also into the battery, of course. So that's basically in a nutshell why MPPT PWMs already are not super efficient. Once the battery is getting fuller, it doesn't really matter anymore because you don't need that power anyway. But don't forget that the battery is not only battery, you also have DC loads connected to the battery. So that power needs to also go into the DC load, not only into the battery. So that's in a nutshell why there are differences. But it's cheap to manufacture, it's easy to switch things on and off. So that's not so hard electronically. In comes the other solar charger, the MPPT solar charger. MPPT means maximum power point tracker. It's more sophisticated because, as the name says, it actually finds out where the maximum power point is. So we have that graph again. Maximum power point sits there. Oh, sorry. So really, this is the actual point. So it finds where it is, and then it will transform a bit like a DC-DC converter. So we'll take the high voltage, so 18 volts DC, make that 12 volt or whatever the battery needs. So it will convert the voltage while leaving the power intact. And it can do that extremely efficient with 98% efficiency. So the full solar power that the panel is producing is all being used. And also, especially when the conditions are not so good. Let's say you have a little bit of cloudy weather, so your current has dropped, so you only have this. It will find the new power point all the time, or the voltage might be a bit different because the panel is heating up. It will keep finding the right power point. It actively hunts for it. And so therefore, it always gives you the best of what the panel at that moment can offer, and not pull it down and not waste 30% like the other one does. So the full PV power can then be used for the battery and for the loads. So if we put that into a little graph, here again we have the amount of power. The unit can run at this power. It doesn't need to drop down. Let's say it was 16 volts maximum power point. It will give that same amount of power to the battery. So now all of a sudden we get much more power into the battery. Before we only got this, and now we get all this extra. So that's basically what it's doing. So it moves the whole power block across. So it's decoupled from the solar panel. So it's like a DC-DC converter, a bit like our DC to DC chargers in a way. Your battery voltage goes low, and in that case we transform up. So that's what we could at. And that was what MPPT became a really popular product. So much so they're being copied in China and all sort of other. Yeah, we're selling so many. It's the 10-year. I think it's the 10-year anniversary this year of selling MPPTs, and I don't know the exact numbers. We sell so many, from small to really big. So when to use an MPPT or when to use a PWM? Like I said, 10 to 40% more solar yield, so 30% on average. So if you have an application where you have only limited space for a solar panel, let's say you have a motorhome or a boat and you have only a few square meters for a panel, go with MPPT because you have 30% more output. So you have really 30% more panel. If you want to go for the low cost option, because PWM is cheap, then you waste a lot of potential power. And power, when you're in a mobile situation, is not always easy to get by. It might mean that you don't need to run the generator so often. So how much is that power saving then anyway? Or you're in a forest because you like to camp in the shade. You have a lot of shading on your panels all the time. You need to move your panel all the time. Go with a proper MPPT. It will charge your batteries quicker. So it's great for non-ideal circumstances like clouds, shade, low irradiance, so low solar, dust in the sky, light cloud cover, that sort of things. You can do a bigger range of panels. So the PWM can only really connect to those 36 or 72 cell panels, can definitely not connect to strings in series. The 60 cell panel, a lot of them can't connect to that either. So there's a lot of limits of what you can do with a PWM. MPPT doesn't have that much bigger input voltage range. So you can go series connected arrays, for instance. One area where the PWM does not does equal to an MPPT is when the solar panels get really hot. So if you, let's say, are in the middle of the desert, although you should really make your solar panels cooler, but if you have solar panels of 50 degrees and stuff like that, then PWM does not make a difference anymore. But in the morning, it's not cold, so not hot. So there's still some savings to be had when you have an MPPT, but it's not that this does better, it just does equal to. That's basically what it does. So that's the difference. So these are the models we have PWMs. They go up to 30 amps, all different types. The Pro, one special one for solar lighting. One for dual batteries and stuff like that. So this for the low end market, but there's still reasonable sales in there. This is, they're not all our own design. Some of them we rebrand because there's just not enough. We rather spend our R&D time on our MPPT solar chargers, for instance. These are the MPPT. So we start at 10 amps and we go all the way up to 100 amps. So there's a really big range in nice little steps. This is what they all look like. So they go from small units, 15. I've got here, for instance, 50. This is the 70 and that's the 100. So they all have more features the bigger the model. Small unit has got a load output. So that's these basically. They have a load output. The bigger ones have remote on off switches. They have a relay sometimes. They have the capability of plugging a display into the front. So there's a lot of different, so the bigger the unit, the more features. And then the really big ones will not only just have VE direct communication, also CAN bus communication. So that's, yeah. But like I said, we talk plenty about what all the models can and cannot do in so many other presentations. There's a really good training online as well. So that's, we'll talk about a bit later. So I want to dwell too much about all the different models, a bit more like what's important to know. First thing you really want to avoid with a solar charger. For instance, a 7515. So 75 in this case is the voltage it can deal with, and that's a hard limit. We can't do more than 75. It's a bit of leeway perhaps, but if you go 90 volts, you will blow this inverter, or blow it up, you'll damage it, and it stops working. And then the other thing is the current. So, but anyway, we're talking about voltage here. So 75 should not be exceeded. Also not when that VOC is applicable. So in other words, early morning, 2 degrees this morning, my panels are cold, sun starts shining on it straight away. I will temporarily get more than this 22 volts slightly. So we always say stay about 10% away. So the first thing, if you have to design a solar array for this solar charger, you take your solar panels, look at the open circuit voltage, does that not exceed what the unit can do? So you basically take 75 divided by 3, that's 25 or something like that. That sits below that 22, that's fine. Or otherwise, 22 times 3 is 66. That's below 75, you're 10% away. Yep, that's fine. So that's good to use. The other thing, the 7515, the other one is current. And this is current that goes into the battery. So output current of the solar charger. And there's one thing sometimes people need to get their head around. So this means that with a 12-volt battery, you can get 15 amps into the battery is 180 watts, 15 times 12. But with a 24-volt battery, you get 15 times 24 is 360 watts. So you cannot, although you might connect to a 360 watt panel, you won't get the full current into the battery unless you upsize and go to a 30 amp unit, let's say. Then you get the full current in. It's just the way our technology works. It's current limiting, and that's, yeah, that's really what it is. So it's rated at output power. So if you, and that's again, often in many situations I say call for 24 volt, and this is another reason. It's much easier to do things with 24 volt. But you can still get a full 360 watt out, but you just need to go to a bigger solar charge. You need to use a 30 amp model instead of a 15. Or 2 15s. You can connect them in parallel without any issues, unlimited. So you can put 100 in parallel if you like, it all goes okay. So I already mentioned it, we do current limiting. And although over voltage will damage our controllers, over current will not necessarily damage it. So if the current gets too big, what we really do is, so this is the rating of the unit. Current is too big, so what we do is you just clip that bit off. So what will go into your batteries will look like that. And there's some benefits with that. Because you can now have maybe a slightly larger array that if it's winter, when you have less sun coming in, so this is your winter curve, it will never exceed, and you'll have the big surface area of your panels to harvest a lot of sun. And then in summer you clip the top off, but that doesn't matter anyway because your sun hours are longer. So your total sorry, your total amount of power is bigger anyway than winter. So this is a way to do that, but you have to watch out. Overcurrent will not cause damage to a controller, it will clip that. But there's 2 scenarios where it can become a problem, is if you have MC4 connectors and you physically go over the current. It's not a good idea to do that. So MC4 connectors don't go over in current. And or MPPTs, they protect against reverse polarity on the solar side. So if you accidentally connected your array the wrong way around, you will blow up a solar charger. It only protects up to its rated current. So that's important to do. So make double sure if you want to go on purpose over, make double sure that that the polarity is right, basically. But to help you with getting the right array, we have a really good solar calculator online. So you can find it if you go to products on our website, and then on the product page, you've got like one little block says MPPT sizing calculator. Click on that, and then you basically, it asks you all sort of things about your panels. There's preset for Victron panels in there, and you can also add from the data sheet all the panel specifics in. So you just go custom, for instance, fill it all in, type how many solar panels you will want to use, and then the calculator will recommend the solar charger for that. It will also, I think it also does yield. So yeah, just have a play around. We still have an Excel sheet in the download section. So if you go to downloads, and then you'll find there an Excel sheet all the way in the bottom. That's basically what's behind this this calculator anyway. Excel sheet can also still be used. We still have that. Some people might be used to that and keep it. That's all fine as well. So either way, the Excel sheet or the calculator. So if you click, everyone gets a copy of this presentation in an email. You can download it from Victron Professional as well. If you go to the PDF of this presentation, click on that link. It will bring you straight to this calculator. Victron Connect, that's how to set it up. And I won't go into all the specifics because that's, otherwise this presentation is going to be 3 hours long or something like that. There's a really good training module on MPPT solar chargers, so do that one. We'll explain how it all works. But basically, in short, you can use Bluetooth or USB. So the unit already has Bluetooth built in, all the smart units have. You use your app, and if you want to do it with USB, you connect to the via direct cable, and you use one of these things, the USB converter, or you plug this one in, and then you have Bluetooth, the smart Bluetooth dongle for via direct. So that's how to connect, or with Bluetooth. You can monitor the solar charger. You can get 30-day data, solar history, accurate like readout of what's happening at the moment. You can set up the units. You can set up the battery charging voltages, the temperature, duration, curve, a lot of really specific things. You can look at the history. It will display errors if there's issues. And also of late, and this is very new, this is only 3 days new or something, we have now why it's not charging in there. So people are sometimes confused that if they go to their system and they see that the solar charger, the solar controller is not charging, why is that? So you now go to the app, you start the app, and then you will see that, yeah, there's not enough voltage coming out of your panel. We, for instance, need 5 volts higher than battery voltage to initiate charging. So it will, so for instance, here it will say insufficient PV power. So it's either night, because then there's no PV power at all. It's really cloudy weather, or there's maybe a cable issue or fuse has blown. So you need to start checking that the PV power is correct. I mean, the PV voltage is correct. And then we also have a little now, and that's new, and we're going to do more of these as well, a little video where Johannes, my colleague, explains why, what you need to check and why we need 5 volts above battery voltage. So at the end of this presentation is a link to that as well. So that's another thing for you to self-study. So, and then some other things you can do with our MPPTs. You can set them up in a smart network. All the Bluetooth, all the smart models. Smart means that they have Bluetooth on board. You can set up with the Victron Connect app to become a network. So you can make a big solar charger out of all individuals, so they all follow the same charge curve. And we have an option, the smart battery sense, a little little dongle type thing, acts as a temperature sensor for the battery, and then you can do temperature compensated charging. So it becomes a really fancy battery. And also this unit can marry it to the smart network. Even a battery monitor, if you had a battery monitor in the system, so BMV battery monitor can also be added to the smart network. So that's that might actually be a presentation by itself. That might be one I haven't done yet, but yeah, smart network. There's a lot of documentation online as well about that. Then the other type, so this was monitoring with your phone with Victron Connect. The other type of monitoring is on the VRM website. So you need a GX device like a color control or a servo. You connect it with via direct cables. I've got one here. Yeah, via direct cables like that. Point-to-point connection. Or if you have the CAN model, you can use the blue cable like this, and then it is a daisy chain. So one to the next, maybe other CAN bus items in the system. And then eventually it goes to the color control. So this is for if you need longer cable runs, can be up to 100 meters away. So this last cable from your system to the control panel can be quite long. While as here, this is a maximum is 10 meters. So that's a difference there. Could be handy. So that's also why we have those CAN bus units. And only the bigger ones, because you're already looking at a big array, basically. Small arrays, you have only one or two small solar charges. So CAN bus or via direct, depending. But anyway, when it connects to VRM, on the display of your GX device, you can read out, you can see all the solar specifics. So it has a little solar icon there and will tell you how much it's generated. For a servo, for instance, you have to do it on your phone with the Bluetooth or online with remote console or go to the same website. But that's again explained all in my monitoring presentation from some weeks ago. And then you can have really nice on VRM. You can actually see the whole solar graph. This was, that was yesterday or the day before. Yeah, cloudy weather. This is my solar output of my own solar charger at home. So that's, so you can do some really fancy monitoring, remote monitoring. Really nice to see if the system is still performing. Yeah, nice thing to do. Grid inverter. So this is the last one. I might continue. I might do the questions at the end. That's probably also easier for the recording. So I'll continue on. So keep hold of your questions. Grid inverters. PV inverter, grid inverter, PV inverter, grid feed inverter. They're called in all different names. Basically, they convert the DC voltage of a solar panel into an AC voltage that's similar to the grid. So they have MPPTs built in, so they do maximum power point tracking, and they have a DC to AC converter in. So basically here you also have the MPPT in the unit, but yeah, well, so it changes DC to AC in an efficient way, 98%, similar to our MPPTs. There's some downsides to it. They need to see a grid to be able to work. So if there's a blackout and the grid stops, then this unit will stop as well. So that's while or DC chargers do not need a grid. They only look at DC. So it's nice and easy. So normally these inverters are used to feed energy back into the grid. So heaps of houses have these everywhere. They have solar power. So you supply the house loads with it. Let's get rid of all this stuff. First, the energy will go into the loads in the house, and anything what's left will go into the grid. That can happen at the same time. So if you turn a big oven on, if you have 5 kilowatt load, then 0 kilowatts will go in the grid. But if you have only 1 kilowatt load, 4 kilowatts will go into the grid, for example. So that's basically what they do. But we can also use them together with multi-plus or quattro to charge a battery. Or when they are set up as an ESS. So there's some things. So there's ESS presentation and off-grid presentation still coming up for systems. So now I'm just going to talk about what they do and how they work with Victron. So there's 2 spots where you can put them if you combine them to a multi. So you can put them on the output on the grid side, or you put them on the multi-output side. 2 different things. This way it works just so in this way it works just like it's a normal grid feed inverter. So sun is shining, it will feed the house loads, and whatever is not being used will go into the grid. Simple. So basically in this scenario, the multi is just a load for the house system. So there's nothing special or weird about that. unless you set it up as an ESS. Then you need a power meter here, you need a GX device, and then you have an ESS. But unless it's ESS, no battery charging will take place, and ESS is coming up in a few weeks from now anyway. The other way to use it, and that's the common way we use a lot for an off-grid system, is we connect it to the output of the multi. Now, when the sun is shining, it will feed the loads. Whatever is not being used will go this way, because energy can't go away. So you can't say energy will get lost or something. If the energy is there, it needs to go somewhere. It's a bit like with water. So energy will start flowing to here and will now go into the battery. So that's how we can charge a battery from an AC source. And then we can even say whatever is left then go to the grid. But again, here we need an ESS. As soon as we allow to go to the grid, we call it an ESS basically. So, but this could also be a generator. It does not need to be the grid. And quite often this thing is off anyway, because if it's a generator and the batteries are full or being filled, there's no need for the generator to run. So, and that I will talk about a bit more in the off-grid presentation as well. So basically that's what it does. But because it is charging the battery, and eventually if this battery was full, a battery can't get fuller, because if the battery gets fuller, it will get, the voltage will go up, things will, the battery will boil, cook, explode, become a dangerous situation. So you need to, there's some special considerations you need to take care of. And also because you have energy, all the energy from here can theoretically go down here, means that this needs to be big enough to create, to allow so much energy feeding in. So that too needs special considerations, which I explain. And one thing I didn't quite put on my slide about efficiencies, this unit is 98% efficient. But if you use an AC source for battery charging, you have more efficiencies than just that. So the energy comes from here, 98, will go into the multi, which is a 95% efficient unit. And then will go into the battery, and depending on the battery technology, you're looking at anywhere between 90 and 75% efficient. So, but let's ignore the battery. Combining AC, so 98 times 95, you end up with 95% of 98, which is probably 90% efficiency or less, maybe even. So this is less efficient as when you were using an MPPT straight into the battery, basically. So anything that goes straight into the battery is highly efficient. But MPPT has the same problem if it has to go into a load. So the choice of what to use when also depends a bit of what's the aim of the system. Is the aim battery charging or battery or backup, or the battery always needs to be charged? Or is the aim, always making sure the load can run? So there is different scenarios. So that's also, and you can already guess, it's possible to combine AC and DC basically for the best of both worlds. So the two requirements, and that's really important to adhere. As soon as you connect the grid feed inverter on the output of the multi, you need to adhere to two rules. One is the 1.0 rule, which means either, whichever is the biggest here, basically no more power can run out of here than this piece of equipment is designed for. So if you have got a 3 kVA multi, we don't really want to see more than 3, maybe kilowatts, but not much more than that. So 3 kilowatts of solar coming in. So you can do two things. You can make sure that your inverter is 3 kilowatts, or you can make sure, let's say you have a 5 kilowatt inverter, make sure that your panels are only 3 kilowatts. So either one, but the total is not allowed, the maximum is not allowed to exceed the rating of the multi. So that's rule number one. The other rule or requirement is that when the batteries are full, we need to turn the inverter off. And we don't do that with a communication cable, but we do that with a frequency shift. And I'll explain what that is. But that needs to be programmed. So you need to run via configure, you need to do the PV assistant, and you need to program that into the system. Because if you don't, we will never turn this unit off, and eventually you get overcharging of the battery. So this is an important one to remember. Frequency shift. Well, what's frequency? That's your AC output, goes up and down in a sine wave. One period is one sine wave. That's 50 hertz. So let's say that's 50 hertz signal. Then the time it takes to do one period is 20 milliseconds. And what we do is we basically make it 52 hertz, and that is an indication that the inverter should turn off. So we increase the frequency, and you need to program that into the PV assistant. And what does a frequency shift look like? That's basically that. So we go from 50 to 52, and then eventually from 52 back to 50 hertz. So we just basically make the sine wave a bit smaller, and then after that we make the sine wave bigger again. This is all explained in some online training material we have as well. So when you use an inverter, AC inverter in Victron system, you have to do that frequency shift, but you have to make sure that the PV inverter actually listens, is actively looking out for that shift. Really old inverters might not. Some old Sunny Boys you needed to set to off-grid mode, otherwise it wouldn't listen to a frequency shift. But one good thing with all the modern certification, and for those people that are in Australia, 4777, as soon as you have the 4777 rating, it just listen for a frequency shift. And for the other countries, they all have their own certification. But as soon as it's a modern inverter, they all have that built in already. But you have to check it, because if it doesn't listen to that shift, then you can get overcharging of batteries, which can lead to explosions, fires, and other nasty things. So that's important. PV inverter assistant. So you need to. The defaults are suitable for Fronius and all the leading brands, more or less. It's always good to double check. So there is a frequency, you have to set a frequency when it starts reducing the output. Oh, sorry, one too high. When it starts reducing, and then the next one, it will be reduced to a minimum when the frequency is that. And it will completely disconnect when the frequency is this. So it is staggered. It's not like on and off. It slowly ramps down and ramps back up. So it's got a certain curve built in. The other thing you have to tell with the PV assistant is how big is your solar system. So you have to type in how much is your solar array, how big is your PV inverter. And basically, and if you put something bigger than the rating of the inverter, you will get a thing, this is not allowed type warning, and it will refuse to program it into your system. This is also to cover our own and your cases where you can say, oh, I didn't know that. That's not if you lie in this, well then you've done the wrong thing, not us. Frequency shift, well, once more, I've explained it a bit already. It's a bit like an animation. So your batteries feed the loads. Your grid feed inverter helps out with that. If the house loads are not so big, your grid feed inverter will go into the battery. Eventually, when the batteries are all the way full, we need to stop. So now we make the output signal 52 hertz. This unit will stop. Once the batteries are discharged a certain amount and it looks at voltage of battery, it will then set the frequency back. So then this unit will go on again, and it will feed everything again. So basically that's how that works. It's fairly simple. So monitoring. So we've got monitoring. So PV inverters, we don't make them ourselves. So you have to obtain a PV inverter. So there's the leading brands like Fronius, SMA, Solar Edge, and ABB. Those, if they are being used and if they communicate to the same network as the GX device does, so they both connect to your same Wi-Fi or Ethernet router in your house or whatever site or situation, then the GX device can find it automatically in the menu. So you have to go to PV inverters and it will show up and go in. And that's all been explained already with our GX presentation, and also it will be in the training segment we have on Victron Professional. So it automatically sees that, and in case of Fronius, you even get little Fronius logo popping up on your display. So we've got dedicated manuals. They're sometimes a bit hard to find, but the easiest spot to find them is in the GX manual. So go there, and there you see links to the 4 inverters, how to set that up with a GX device. So the important, both need to be on the same network. Especially in off-grid, in ESS, we use a bit of information, but quite often we don't actually do anything with that PV information. We only really display it onto the screen so you can see what solar is coming in. We don't really use that for any calculations, maybe in the future, but at the moment not. It's only making sure you can see it. Then if you have a solar inverter that is not on the list, then you need to put an energy meter in. So if it's on the input or the output, you put energy meter in. So I've explained that also not so long ago. These are the energy meters. Oh, little clip is falling off. And it talks to the GX device with an RS485 to USB cable or with a wireless option called Zigbee. And we have some more things coming as well. We have a click-on clamp meter in the planning, and we have a Wi-Fi version of this in the planning. So we will come out, over the course of this year, I hope, with some more energy meter options, because this wire can be a bit of a nuisance. The Zigbee would be much nicer if this had Wi-Fi built in or an Ethernet port on there. You can use it straight away. So that's in the making. But for now, you have to use the energy meters, and it's also still possible to use the current sensor. But again, go to the GX manual, go to the link PV inverter monitoring, and then you get this little table, and there you can click on all those blue tags to get energy meter info and or current sensor information. And energy meter is used if you have an ESS. It can also be set up as a grid meter. But again, I'll talk more about ESS when we get there. Yeah, and that's sort of the tail end of my presentation. So AC versus DC, what's better? Yeah, DC is more efficient, less conversions, especially for battery charging. Remember that you have 2 conversions potentially if you use AC. It's better for battery charging. It does a much nicer job at battery charging. It does bulk absorption float. You can tailor it so nicely to battery. It's like having a really high-end charger connected to your battery versus something that will just connect on high and low voltages. So that's the difference. It's very easy to set up. It's no assistant programming. There's not the power limit. So the 1.0 rule does not apply. So no rule. You can do as much solar as you like, as long as your batteries can take care of that much solar. It will work during a blackout. Remember that the AC inverter needs grid to work. And it does not rely on the multi generating the grid. The multi in a system with an AC coupled inverter is the grid generating inverter. So the multi generates the grid, and the PV inverter latches onto that and then starts working. But if the multi is off because of low battery or something like that, then in the morning you might have solar coming in, but nothing will happen because the multi is off on low battery. Solar might be there, but it's not being used because there is no grid. So that's why it pays to put a bit of DC, at least in even a big AC coupled system, just to get like the black start scenario, to get out of that. Benefits of AC is higher voltages, but this is, we have something soon as well where DC, yeah, we're going to make higher voltages DC MPPTs as well. But yeah, so higher voltages lead to bigger array. So more panels in series, easier to wire, and your PV cables are thinner. So basically the higher voltages, that all causes this as benefit. So that's really not so much benefits, and especially, especially now we're gonna come out with a 400 MPPT in a few months, hopefully, or maybe end of this year. It depends a bit. The whole Corona throws things off a bit, but there's prototypes out there. I think one guy in North New South Wales is already trying one, and yeah, so that's they are imminent. Oh, well, geez. But so 400 volt MPPT, and then basically this whole thing doesn't apply so much anymore. So you can go totally DC, and you have the best of all these options. That yeah, we'll see. As soon as the first one is there, I'll order one, I think, already. Because I was about to put a CPV on my house, but I might actually go. So if you have storage, I mean, if of course for grid feeding, if your aim is grid feeding, AC is much better. But if your aim is storage or riding out blackouts or really full end ESS, semi off grid, then yeah, 400 volts is really good. So downsides of DC is yeah, the lower voltages until we get this. The downsides of AC is that you always need to do programming. You need that frequency shift. You have the 1.0 rule. It's less suitable for battery charging. It's really great for feeding back to the grid and supplying loads. So if you're let's say you're designing an off-grid system with heaps of AC loads in there, and you really want that supplied by, yeah, of course, then call anything that's already needs to be in AC, keep it in AC. That's really, so battery charging go DC, feeding AC loads go AC. That's basically the guidelines there. Depending on what inverter you have, you might need an energy meter in there, so that's an extra component. But otherwise, stick with the Fronius or the ABB, etc., etc. And it does rely on the multi-generating an AC. So black starts in the morning after your battery's gone dead, then AC is not for you, but a combination would be for you. So a combination, no problem at all. So you can easily connect both AC and DC to your system. And that's probably the preferred way. Small systems stick with DC, bigger ones put AC in there. Yeah, training and more info. So I mentioned it a few times already. See, because this presentation already took over an hour, and that's just the basics. MPPT and ACPV, those two are basically, once you finish watching this one, you should watch those two. I think it's about half hour of video presented by Kai, explaining exactly how to set up MPPTs, and then the same for AC. Do the test afterwards, and then you get a little certificate as well. It's almost compulsory after this one to do those two, because I don't really want to do everything double either. So that's why I chose topics that are not covered so much. I mean, there's overlap, but yeah, so I've been a bit more theoretical rather than practical. Also, since last week, we now have training available in a whole lot of different languages. So if your native language is not English, go try it in a different. It's basically the subtitles we have now on the YouTubes. The exam at the end is in the different languages. So that's So go to Victron Professional, click on online training, and then you get your whole list of all the different trainings. So you want to look for those two, or click on this link. Brings you to Professional, you get there as well. Apart from the training, we have some other stuff as well. We have now that little movie I said with Johannes, who explains why you need 5 volts higher to initiate charging. That's one of them. We have a webinar that explains about Fronius and Victron. Those can both be found on our, I think on our YouTube channel, but also in Victron Professional. There's I'll go back one. There's a video link. Click on that. You'll get all of training videos and these sort of random, accessory videos. And then we have some interesting articles about topics that have to do with solar. So we have a blog story, matching solar modules to MPPT charge controllers. That's an interesting one. It talks about the solar calculator sheet and stuff like that. PV panels shadow effect. That's a nice blog story that actually came from one of our community posts. What does shadow do to a panel? Read it, quite interesting. Then we have a white paper, which is this one here, which solar charger, PWM or MPPT, that basically explains what I've explained in this webinar. And then a lot for the AC stuff you'll find in the GX manual for PV inverter monitoring. For those people that don't know, because it's a bit hard to find, that's the link to it. So just go to the GX manual. Yeah, so past recordings. This is another thing that I get a lot of emails. Oh, yeah, I've missed your presentation, and can I have the links to the old ones? They are all in Victron Professional. If you click on events, you get a list of all your training events, my events, but you also have an extra little link that's a bit hard to find. We might change and make that better visible. Past event videos. If you click on that, you get to a screen that looks like this. It basically has all my past videos, but also some of my colleagues' videos are now coming in, and especially the different languages. There's some German ones, there's a French one or a Spanish one in there. So eventually we populate that with all the webinars. And yeah, that Corona could stay some while. So there might be more webinars in the future as well. So that's how to get my past event videos. It's really easy. And they stay in there for a long time. Well, and then this is the last slide. So next webinars. Next week, I'm going to talk about, and this is really, this plus these four is actually almost a series by itself. So today I explained the basics. Next week, I'm talking about how to design a system, calculate and commission. So basically we've gone, once I start with this, I've done all my basic components, and now we put it together for a system. So we explain how to make the system, how to do the system power calculations, how big should the batteries be, how much solar do I need, all that sort of stuff is being talked about, and how to commission, so the whole design process, all the way up to installing it and then giving it to the customer. The one after that specifically talks about off-grid systems. The one after that about ESS systems. And then last, I'm going to do a little bit about troubleshooting and warranty. System troubleshooting, but also product troubleshooting a little bit. I'll just have to make that one still. The other three are half done. But yeah. So I will say see you next week. Same time, same day, same time. So that's it for today. Okay, thank you.
Very good, Marguerite. Yeah, next week's system design, I think, will be interesting for a lot of people. So hopefully everyone